Next we are going to study about what are the other methods of preparation for alkyl halides and aryl halides. So in the previous video we studied about the preparation of alkyl halides from alcohols. From alcohols we can prepare only alkyl halides, not aryl halides. So the first preparation method was from alcohols. Now the second method of preparation is from hydrocarbons. What is meant by hydrocarbons? Yes, compounds containing carbon and hydrogen only. There will not be any nitrogen, oxygen, sulfur or halogen or any other atom other than carbon and hydrogen. So from hydrocarbon, the first method is by free radical halogenation. We know already we have studied about this free radical halogenation in class 11. Free radicals are produced. We know that free radicals are produced only when there is high energy radiation or high heat energy. So free radicals are produced only in presence of heat or light. Now during the free radical halogenation or under the free radical halogenation reaction, only we are studying about free radical chlorination and bromination only. There is no iodination or fluorination. So under free radical halogenation we have free radical chlorination or free radical bromination. The reagent required for chlorination is chlorine in presence of heat or light, and for bromination the reagent required is bromine in presence of heat or light. So heat or light is the necessary condition for the free radical halogenation. Here we are studying about the free radical chlorination or bromination of alkanes. Alkanes means what? These are the compounds containing only carbon-carbon single bonds. So they are hydrocarbons containing only carbon-carbon single bonds. So we are going to study about the free radical halogenation of alkanes only, and during this free radical halogenation of alkanes we are getting isomeric monohalogen derivatives. Isomeric means what? You will be getting different products, but the molecular formula will be same. Monohalogen derivative means what? Yes, containing only one halogen. So how we can get a monohalogen derivative from an alkane? Yes, by replacing only one hydrogen from alkane by a halogen. So remember, after the free radical halogenation of alkane, we are getting the products as isomeric monohalogen derivatives. For example, CH3, CH2, CH2, CH3. Above the arrow it is written as chlorine and sunlight. H nu is representing sunlight. So organic reactions we have to identify from the reagents written above the arrow. So since here chlorine and sunlight is written, the reaction taking place will be free radical halogenation. Now look at the reactant molecule given here. So here the basic reaction taking place will be any one hydrogen will be replaced by chlorine. If you look at the structure of the given molecule, we can see that there are two types of hydrogen atoms present. One is CH3 hydrogen and the other one is CH2 hydrogen. So the first possibility or first possible product will be, I am replacing one hydrogen from CH3. So it will become CH2 Cl, CH2, CH2, CH3. Now the second possibility is by replacing, I am replacing one hydrogen from the second type of hydrogen, that is CH2 hydrogen. So the formula will be CH3, CH2 will become CHCl, CH2, CH3. If you write the products, if you write the name of these products, you will get it as 1 chlorobutane and 2 chlorobutane, two different compounds, but the molecular formula is same. So that is why it is said that isomeric, and only one hydrogen is replaced at a time. So that is why it is known as isomeric monohalogen derivatives. Now there is no other possibility to replace any other hydrogen from here. If you replace one hydrogen from here, from this CH2 you will be getting same as the 2-chlorobutane. From here if you replace, you will be getting same as this one. So how many isomeric monohalogen derivatives from this? 2 products. Now if you look at the next example, that is actually exercise 10.3 in your textbook. Here also above the arrow it is written as chlorine presence of sunlight. So the basic reaction taking place here is free radical chlorination. At a time it will be replacing one hydrogen. One hydrogen will be replaced by one chlorine. So look at the different types of hydrogen atoms present. Here we have CH3 hydrogen atoms which is attached to CH group. And here we have CH hydrogen, then CH2 hydrogen. Here also there is one CH3 hydrogen, but this CH3 hydrogen is entirely different from this because that is attached to different carbon atoms. So first possibility I am writing by replacing one hydrogen from here. So what will you get? CH3 twice, CH, CH2, CH2, Cl plus the second possibility from CH2 hydrogen. So CH3 twice, CH, CH2, CHCl, CH3. Now the third possibility is from CH hydrogen. So CH3 twice, C, Cl, CH2, CH3, and the last isomeric monohalogen derivative from hydrogen I am replacing from any one of this methyl group because these two methyl groups are same because both are attached to same carbon. So it will become, I am replacing hydrogen from only any one CH3 group, so it will become CH2Cl, CH, the another CH3 will remain as such, CH2CH3. So here from this hydrocarbon we are getting, from this hydrocarbon alkane we are getting 4 isomeric monohalogen derivative. So this is the first method of preparation from hydrocarbons by free radical halogenation. Now the second method of preparation from hydrocarbon is by electrophilic substitution reactions. Already we have learned in class 11 there is 5 different types of electrophilic substitution reactions are there. So among the 5 reactions, here we are dealing only with halogen compounds. So what we require here? Yes, only halogenation. And which are the halogenation we are doing here? Yes, only chlorination and bromination. Now we know what are the reagents required for the halogenation. Halogenation, which halogenation? Electrophilic substitution reaction. For example, for chlorination, the reagent required is chlorine in presence of anhydrous AlCl3 we can use, or we can use ferric chloride also. If we are using bromine or if we are doing bromination, bromine in presence of ferric bromide or FeBr3. Now, other than anhydrous AlCl3 or FeBr3 or FeCl3, for chlorination and bromination, for both we can use iron as catalyst, but the reaction should be carried out in dark. So that is about the reagent for electrophilic substitution. See the first example here I have taken benzene only. There is no other group present in the benzene ring. Benzene, it is an example for a hydrocarbon, isn't it? There is no other atom other than carbon and hydrogen. And see the reagent required here, chlorine in presence of anhydrous AlCl3. If it was chlorine in presence of sunlight, it will be free radical halogenation. But here, what is written? Chlorine in presence of anhydrous AlCl3. That means the reaction taking place here is electrophilic substitution reaction. Then what is the difference between electrophilic substitution and free radical halogenation? Remember, in free radical halogenation, hydrogen will be replaced from the chain But during electrophilic substitution, halogen will be introduced to the ring by replacing hydrogen. Remember once again, during free radical halogenation, halogen will be introduced to the chain by replacing hydrogen. But during electrophilic substitution reaction, halogen will be introduced to the ring by replacing hydrogen from the ring only. So here it is benzene ring. If it is simple benzene ring, we know that yes, all the 6 positions are equivalent positions. So we can introduce chlorine to any position. So we are getting it as chlorobenzene, and we know exactly what is happening here. So what is exactly happening here from any one position? Hydrogen plus chlorine, it will be eliminating as HCl, that we have already learned in class 11. So here we no need to represent all those things, we can directly write it as chlorobenzene. But if you look at the second structure, second example, it is not simple benzene ring containing methyl group. What is benzene ring containing methyl group? It is methyl benzene, or yes, we know that it is toluene, but still it is a hydrocarbon on reaction with bromine in presence of iron or in dark. So here also the basic reaction is electrophilic substitution reaction. So bromination will be taking place, but there is methyl group already present in the ring. So here we have to see the directing influence. And we know that the alkyl groups are, methyl group is an alkyl group, and all the alkyl groups are ortho-para directing and activating. So the product will be, Cl will be introduced to the ortho position, so orthochlorotoluene, and the second possibility is chlorine will be introduced to the para position. This is the para, ortho, meta, para. This is the ortho isomer and this is the para isomer, and we know that the ortho will be the minor one and this will be the major one, and we are getting aryl halides, isn't it? So by electrophilic substitution reactions we can prepare aryl halides, not alkyl halide. There is no electrophilic substitution in aliphatic compounds. It is a characteristic of only benzene ring containing compounds or aromatic compounds. Okay, so we can prepare only aryl halides. The only thing is, if there is any group already present, we have to see the directing influence. Now, the next method is the very important reaction, the first named reaction coming in this chapter, that is Sand-Meyer's reaction. And remember, this is also only for the preparation of aryl halides. So the first method by electrophilic substitution reaction, and the second method for the preparation of only aryl halide is Sand-Meyer's reaction. And see, what is the first? We have to study the reagent required for Sand-Meyer's reaction. It is NaNO2 and HX. NaNO2 is known as sodium nitrite, ITE. Sodium nitrite along with HX. HX means it can be any halogen, but usually we are using HCl. Followed by treatment with Cu2X2. Cu2X2 is known as cuprous halide. X can be only chlorine or bromine. Now we will see the reaction. When an aromatic primary amine, aromatic means containing benzene ring, primary amines means the functional group will be NH2. When an aromatic primary amine, what is the name of this compound? Yes, aminobenzene or aniline. So when an aromatic primary amine, when it is dissolved in cold aqueous mineral acid, for example HCl. Why it is mentioned as cold aqueous mineral acid? Because the condition required for this reaction is this should be carried out, or the aniline or aromatic primary amine should be dissolved in HCl under cold condition. The temperature required is 0 to 5 degrees Celsius or 273 to 278 Kelvin. So first we have to dissolve the aromatic primary amine in cold aqueous mineral acid like HCl usually. Then we have to add sodium nitrite NaNO2. So the first step is it is treated with NaNO2 and HCl. Okay, so temperature is 0 to 5 degrees Celsius. So we are an aromatic primary amine, we have to dissolve in cold aqueous mineral acid like hydrochloric acid. Then we have to add sodium nitrite. So here when we do this, what happens here is the NH2 group will be converted to N2 plus X minus. So if we are using HCl here, so first I will write generally HX. So what happens, the NH2 group will be converted to N2 plus X minus, where N2 plus group is known as diazonium group. So how we can write the name of this product as benzene diazonium halide. And this is the first step in Sandmeyer's reaction known as diazotization. So diazotization is actually the preparation of diazonium salt. And remember, the diazonium salt should be prepared only under cold condition. And how we are getting diazonium salt, or what is diazotization? When an aromatic primary amine, when it is dissolved in cold aqueous mineral acid like HCl, and when we treat with sodium nitrite, we get benzene diazonium halide. If we are using HCl, we will be getting benzene diazonium chloride. Now, in the next step, the benzene diazonium halide N2 plus X minus, we have to treat with Cu2X2. What is Cu2X2 known as? Cuprous halides, where X can be only chlorine or bromine, because only chlorine or bromine we can prepare using Sandmeyer's reaction. So what we get is this N2 plus will go as nitrogen gas, and we will be getting halobenzene. That means if the X is chlorine, we will be getting chlorobenzene, and if X is bromine, we will be getting bromobenzene. So we started the reaction with aniline and we got chlorobenzene or bromobenzene. So very important point, Sandmeyer's reaction is actually the conversion of aniline to chlorobenzene or bromobenzene. That means how we can replace NH2 group by halogen. This is the reaction once again. So how we can define Sandmeyer's reaction as when an aromatic primary amine, when it is dissolved in cold aqueous mineral acid, and when we treat with sodium nitrite, gives benzene diazonium halide. And this reaction is known as, the first step is in Sandmeyer's reaction is diazotization. And in benzene diazonium halide on reaction with cuprous halide, we get chlorobenzene or bromobenzene, and this reaction is known as Sandmeyer's reaction. So here also remember, X can be chlorine or bromine. Now from this, if we want to prepare from a benzene diazonium salt N2 plus X minus, if we want to replace the diazonium group by iodine, we know that iodine is larger in size. Due to larger size of iodine, this diazonium group can be easily replaced by iodine by simply shaking with potassium iodide. But remember, this is not Sandmeyer's reaction. Sandmeyer's reaction is only using cuprous halide. So how we can prepare iodobenzene? It is by simply shaking with potassium iodide. We get iodobenzene and N2. So note down, this is the conversion of aniline to iodobenzene. So aniline first we have to convert into benzene diazonium halide, then simply by shaking with potassium iodide. Why simply by shaking with potassium iodide? Because Due to larger size of iodine, it is very easy to replace by iodine because the bond strength is weak. So this is about the preparation of aryl halides by Sandmeyer's reaction. So that is about the preparation methods of alkyl and aryl halides from hydrocarbons. Now from the next type of hydrocarbon, that is alkenes. What are alkenes actually? Yes, they are hydrocarbons containing at least one carbon-carbon double bond. Here, the first we will see. So how we can prepare halogen compounds from alkenes? Yes, by the addition of HX. Addition of HX to alkene. And already in class 11 we studied that addition of HX to alkene follows according to either by Markovnikov's rule or by anti-Markovnikov's rule, only if it is an unsymmetrical alkene. If it is a symmetrical alkene means what? The double bond will be present between same type of carbon atoms. For example, CH2 double bond CH2 on adding HBr. In the case of symmetrical alkenes, no need to see the Markovnikov's rule, isn't it? So to symmetrical alkene, how we can add HBr? HBr on ionization, we are getting H plus and Br minus. We can give hydrogen to any carbon and Br minus to any carbon. And remember, after addition, don't forget to change the double bond to single bond. So the product will be, I am giving H plus to here and Br minus to any carbon we can give because it is a symmetrical alkene. So it becomes CH3 single bond CH2 Br. There is no major and minor product, only one product we are getting here. Now the second one is also a symmetrical alkene because the double bond is present on same type of carbon atoms. And here we are adding HCl, another HX, so on ionization H plus and Cl minus. So here H plus I am giving to this carbon and Cl minus, the negative part to the other carbon, and the product will be CH3, CH will become CHCl, double bond will become single bond CH2, CH3. This is actually CH3, sorry. So this is about the addition of HX, HCl or HBr or HI to any symmetrical alkene. So to any carbon we can give the positive part and to any carbon we can give the negative part. But in the case of unsymmetrical alkenes, the addition of HX to unsymmetrical alkene takes place only according to Markovnikov's rule. What is Markovnikov's rule? Yes, when we add HX to an unsymmetrical alkene, X minus should be attached to the more substituted carbon. More substituted carbon means the carbon with less number of hydrogen. That will be the major product and the other one will be the minor product. So see the first example, CH3, CH double bond CH2. So here it is not a symmetrical alkene, it is an unsymmetrical alkene. Now HI on ionization H plus and I minus. So according to this we have to add according to Markovnikov's rule. So the negative part should be attached to carbon with less number hydrogen and positive part to carbon with more number of hydrogen. So the product will be as the major product. So CH3, CHI, double will become single CH3 and this will be the major product plus, write the other one as the minor, CH3, CH2, CH2I will be the minor product according to Markovnikov's rule. Now the next example is actually 10.4 in your textbook exercise. So here also plus HBr is given and HX is given and on the left hand side an alkene is given. Don't add HBr to here, this is not an alkene, this is benzene ring, looks like unsaturated but it is saturated. So we have to add HBr to this double bond, HBr on ionization H plus and Br minus. This is the double bonded carbon we have, one is CH and the other one is CH2. So H plus should be attached to positive part carbon with more number hydrogen and negative part carbon with less number hydrogen and the product will be benzene ring CHBr, single bond, CH2 will become CH3, will be the major product. And what will be the minor product here? Benzene ring. To this carbon we have to give hydrogen, so it will become CH2 single bond CH2Br, and this will be the minor product. Now see the next example. Another unsymmetrical alkene is given and we have to add HCl according to here, note down. This is according to Markovnikov's rule. This is also according to Markovnikov's rule because unsymmetrical alkene. So HCl on ionization H plus Cl minus. So positive part to carbon with more number hydrogen and negative part to carbon with less number hydrogen as major product. So it will become CH3, CH2, CHCl single bond CH3 as major plus CH3, CH2 single bond CH2Cl as minor product. Now, if an unsymmetrical alkene is given, to add HBr in presence of peroxide, if there is only HBr present, we can add according to Markovnikov's rule. But if peroxide is written above the arrow, it is known as anti-Markovnikov's rule. Already we have learned in class 11, that is also known as peroxide effect or Karash effect. How the addition of H and according to anti-Markovnikov's rule, in presence of peroxide, we can add only HBr. Any HX we can add according to Markovnikov's rule, but according to anti-Markovnikov's rule, we can add only HBr in presence of peroxide. And how the addition of HBr in presence of peroxide? Just opposite to Markovnikov's rule. That is why it is known as anti-Markovnikov's rule. The negative part should be attached to carbon with more number hydrogen or the less substituted carbon as major product. So here, if you look at the reagent given plus HBr in presence of peroxide, so we can identify that it is according to anti-Markovnikov's rule. HBr on ionization we are getting H plus Br minus. Look at the double bonded carbon, one is CH and one is CH2. So according to anti-Markovnikov's rule, Br minus should be attached to carbon with more number hydrogen and H plus to carbon with less number as major product. So the product will be benzene ring, CH2, CH2, single bond CH2Br as major plus benzene ring, CH2, CHBr and CH3 as minor product. Now there is a few back questions also according to based on this. CH3, CH2, CH double bond CH2 plus HBr in presence of peroxide. So it is anti-Markovnikov's rule. HBr on ionization H plus and Br minus. Br minus to carbon with more number hydrogen and positive part to carbon with less number hydrogen because it is anti-Markovnikov's rule. So CH3, CH2, CH2 single bond CH2Br, that is major, plus minor product will be CH3, CH2, CHBr single bond CH3. Similarly, there is one more equation. CH3, CH double bond CH3 twice, again an unsymmetrical alkene. We have to add HBr, but there is no peroxide given, so it is according to, yes, Markovnikov's rule. Now how we can add? According to Markovni, the negative part should be attached to carbon with less number hydrogen and positive part to carbon with more number hydrogen as the major product. So CH will become CH2 single bond CBr, CH3 twice as major, and The minor product will be CH3, CH, CH2, single bond, CH, CH3 twice as minor product. So this is about the preparation of alkyl halides from hydrocarbon, that is alkene.